And let's start the recording. So we have the course of Advanced Computer Vision. Yep. So before we start the first lecture, let's just start with the course presentation. Let me share the screen. There it is. So the course is practically called Advanced Computer Vision, but it highly depends on the level of the students already. So I gave this course to well, 3 different backgrounds. Well, one was the second year Masters of Data Science guys, and I guess they were a bit the most advanced people who took this course. So for them, we went ahead very quickly with the revision for machine learning concepts such as linear regression, logistic regression, and these things, because they're very important for us later on during the course. And yeah, we went to stuff such as object detection. We went through deployment. We have seen stuff such as interpretability and object detection, as we said, object segmentation and stuff like that. But for the other group, for example, the data science masters first year, we spent a little bit more time in the first lectures on basic computer, what is it called, neural networks. And then when we were studying about the course of interpretability, we spent a little bit more time also revising basic machine learning concepts. And I think the ones which were most beginners were the software engineers who took this course. So basically we had a couple of, I think last semester, we gave this course for the software engineers second year masters, or first year masters, and they have never taken any course about machine learning. Hence, we did everything from scratch, right? So again, this course is going to be very flexible depending on your level, guys, and even the concepts or the content will vary depending on what are the things that you guys prefer to learn about. So the course title is Advanced Computer Vision. It's done in F21 University, and my name is Coach Imaduddin Ibrahim. You can call me Imad. No need to use professor because I don't have a PhD, and no need for lecturer and stuff like that. So just be friends, right? There we go. So small self-introduction. I have a bachelor's in computer science from Algeria, and then I did my master's in data science in F21 University. And currently I'm doing my PhD in artificial intelligence in Sorbonne University. Here it is, quite beautiful, in Paris. From like an industrial experience point of view, I've worked in a couple of the Innopolis research labs, such as the machine learning and knowledge representation lab with Professor Khan. So started doing like a couple of research there, and then I became kind of like the manager or like his secretary, you would say, right? So I was mentoring the students in the lab who are doing their thesis or like doing some research papers. And from there, I went to the industrial artificial intelligence lab, and we worked on medical computer vision, right? So medical imaging and stuff like that. And we published 2 papers, very nice papers, and the last paper is submitted, but we still don't have the review. So this is from like research point of view in Innopolis. From like industrial point of view, I've worked in like companies before going to Russia, in French companies mainly, but it was not related to data science. So working as a mobile developer or a web developer. And then when I came to Russia, directly, I started working with Provectus, which is a company in Technopark. I did there my internship, and then I started working with them. And with them, I worked mainly on computer vision projects. So some of our bigger projects were some mask detection projects. So that was deployed somewhere, I don't know where, and a helmets like for construction sites and like some I don't know, those things that reflect the light for construction sites, and that was deployed in a couple of places in Germany and Switzerland. And so yeah, so it's like object detection and image segmentation. And now I am currently working with Pepsi as kind of a data scientist. So this is maybe like the most interesting job. So Pepsi does have a lot of volume of data. So you can imagine the different sales, the different ads that Pepsi runs. And they would like to basically analyze all of this data and make sure that they're spending money in the right direction. And this is what we do as a team. So this job is a bit more intensive than the others. So previously in most of the companies that I've worked with, it was just me as the team of data science. But now we're working in a team of 50 people, just us, like just working on one task. So definitely the scale is a bit higher. My research interests, of course, computer vision, as that's the field that I'm working on mostly. The second field is domain adaptation. For those who took the Professor Khan's course on machine learning, I'm assuming you already know what domain adaptation is, because domain adaptation is mainly like the main area of interest of Professor Khan. That's the thing that he does most of his research on. And to put it in simple terms, basically it's transfer learning, but with a bit more steps to it, right? So you have two big data sets and you're trying to improve the results of your models on the second data set, or like the smallest data set. But instead of just training on the first one and then training on the second one and call it a day, now you're going a bit further. So you're trying to combine both data sets in a heuristic or in some sort of an adversarial learning in order to improve the results even further. So we're definitely going to see a couple of applications of domain adaptation and generative adversarial networks, and how can we use this adversarial concept for images in general. The final part is knowledge graphs. So this is my current thesis or PhD thesis. So it's basically combining knowledge graphs with domain adaptation in order to improve computer vision models. What knowledge graphs are very simple concepts. So basically, let's imagine, for example, the Mona Lisa. So you have the painting of the Mona Lisa. That's one concept that is related to another concept such as Da Vinci. The relationship is Da Vinci painted the Mona Lisa. Mona Lisa is currently in, for example, Louvre Museum in Paris. Louvre Museum was created or built by some king. So this is another concept. So this is what knowledge graphs are, right? So knowledge graphs are just a way to represent data that is very rich in these relationships between the different concepts. And yeah, that's it. So this is me in general. If you guys want to contact me, this is my Telegram. I highly don't recommend sending me emails because I don't really respond that much. It's just harder to reply on emails than it is to reply on text messages. So just send me a text message on Telegram and I respond pretty fast. I will update this link to basically send you guys to the Telegram group that you are in. I'm sure most of you guys are there already. How are we going to evaluate you after this course? So I know that the grades of this course can influence basically how much money are you going to get for the next semester. So usually all of the students either get an A or a B. Only those who really do not show up or do not give any effort, they get like a C. So basically, yeah, the final project is going to have like 30% of the grade. So you can do like a paper presentation, or you can do a paper publication. You can build some sort of a product, or if you are already working on like some field that you're interested in, and you saw that there is like a library with some issues, like some bugs that you could fix, just contact them and fork their library, implement or fix that issue, and try to get that pull request accepted. So this is like the ideas that you could have for your final project. The mini projects, we're going to have like 4 in total or 3 in total. And yeah, so if we have like 3, we will count all 3 of them. If we have 4, then we will count only the best 3 of them. These mini projects are usually just like, I give you some lab, and basically I'm going to ask you to go home and reapply the whole lab on a different data set. Very easy mini projects, always submit them the same weekend. It's much easier for you guys. For exams and quizzes, so we're gonna have as many quizzes as possible. And we will take the top 5 of them. Again, if we have only 5 quizzes, then we will take all 5 of them. And if we have more than 5, we will take only the top 5 quizzes for every single student. The grades for the quizzes is gonna be like 15% of your grade. So for those who do not attend the lecture at all, at least they have said completely goodbye to an A, right? But they still have some chances to get B, right? And then we have like 2 exams. The first one is the midterm exam on 10% and the final exam on 15%. The exams are going to be very, very similar to the exams from Professor Khan's structure. So yeah, expect the same thing, right? There's not going to be a practical part for our exams. So basically only a paper exam. Nice. Yeah. The outline of the course, again, the course is mainly intended for second year student masters. So people who are going directly to either work in the industry or who are going directly to, for example, teach or do research in the university. So I'm going to try and give you as many theoretical concepts or theoretical knowledge as possible for those who are going for teaching, and give you as many hands-on project experience with computer vision projects for those who are trying to go to the industrial part. First, we will start to speak about like classification. So we will speak about neural networks in general and 2D CNNs, and then we will speak about 3D CNNs. We will also speak about interpretability in this part, or in this first part. So we will definitely touch on concepts such as decision trees and logistic regression, since they are kind of the core concept for interpretability and explainability. The second part will be object detection, where we will see like different architectures such as the RCNN family, RCNN, fast RCNN, faster RCNN, and mask RCNN. Of course, they're all implemented in the Detectron library. And then we will have the YOLO versions, right? So we will speak about only YOLO version 3, YOLO version 4, and YOLO version 5. YOLO version 1 and 2 are kind of like history for now. Later on, we will maybe like the second half of the course, we'll speak about advances in computer vision in general. So we're definitely going to touch up on GANs. We'll speak about, as we said, domain adaptation. Basically, we'll focus mainly on this A part of the GANs, so the adversarial part of the training. Sorry. We will speak about object tracking, how it's done, definitely facial recognition and stuff like that. So these concepts, they're up to you guys. We can cover as many of them as you guys want, right? So if you're interested in maybe facial recognition more than GANs, we can skip GANs and go to facial recognition, spend more time on it. And later on in the final week, this part is not going to be evaluated. So this is just like a bonus part. You can think of it like as extra, right? So here we will be speaking about deployment. We will speak about stuff like, let me just check the group. Okay, yeah. Okay, Firas. Was he able to join? Yeah, I think he's here. No, he's not. Okay, cool. As I said, the final part on deployment will cover stuff such as Streamlit. So it's a library that allows you to build websites pretty quickly. It's quite useful for those who are going to be working with different clients. So it allows you to give them like access to your model very quickly and show them how things are done or how your model's performances are. We will speak about how to use Docker containers for different components. Of course, these components will be part of the Kubeflow pipelines. So we're going to speak a lot about what pipelines are and how can we use them to train, evaluate, and deploy our models on more larger scale, of course. And yeah, we're going to speak also about like Flask and RESTful APIs. So now I think it's about time. Now we had like a cool introduction to me and we got to know my background. Now I would like to expect the same from you guys. I would like you to basically every person just opens the mic and goes ahead, tells me what's their name, what are they studying, what's their background, are they familiar with like sklearn, NumPy, PyTorch, TensorFlow, CUDA, darknet, all of these different data science libraries and frameworks. And of course, tell me if you have some industrial experience. Tell me if you have if you're working already in a company. So I think if you're already in the second year, you should either be working in a company or doing some research with some professor. So that could be interesting information to know. And yeah, tell me a bit about your bachelor background. Do you have some experience already with computer vision or completely new to it? Yeah, all of these concepts, right? Go ahead.
Hello.
No?
Yeah, can you hear me?
Yes, we can hear you very well.
Okay. Nice to meet you.
Nice
My name is Randall.
Nice.
I am from India. I just joined actually for my first year master's in data science at Innopolis. And my bachelor's was in earth science and computational seismology, basically like decomposition of signals, like earthquake signals. So that was kind of interesting.
Wow.
And I did an internship in traditional computer vision, like 1D edge detection for accuracy in measurements for industrial instruments. And after that, I gave this exam for Innopolis. Now I'm here. My background, I have, I'm okay-ish in like NumPy and Pandas and superficial idea of TensorFlow, and no background in PyTorch, and very minimal in computer vision. So that's all. Thank you.
Nice. That's a very interesting background. Yeah, it's pretty interesting. Are you already in Innopolis or you're still in India?
I am currently in India. I just received my invite, so I should be there in less than 2 weeks.
Okay, nice. So you have never taken the course of Professor Khan on machine learning? Kind of new.
I'm taking that course right now. Yeah. Yeah, thank you.
Nice, you're welcome. Someone else? Go ahead, guys. Don't be shy.
Hi. Yeah, I'm second year master's in robotics right now here in Innopolis.
Nice.
My bachelor was also in robotics in Russia, in St. Petersburg.
Cool.
If you're speaking about computer vision, I had courses machine learning here with Khan, and we had computer vision with Fahim for the previous semester.
Nice.
So I have kind of experience with all of these libraries and all of that stuff. And currently my thesis, my research is with neuroscience. Also working with
Professor Suchi?
No, with Suchi, it's with Frolov, Nikita, Khramov, like that stuff.
Yeah, cool. So working with that EGG thing, right?
Yeah.
Yeah, cool. Good luck with that.
Thank you.
So do you have some experience with PyTorch?
Yeah.
Nice. Do you have experience with darknet?
Also, yes.
Nice. So
we did the project, yes, using that.
Okay, that's very nice. So you're kind of similar to the first group that I was talking about, like the data science master's second year, who have already taken the computer vision course from Professor Fahim and the machine learning course from Professor Khan. So that's nice. Good. Good to know. Anyone else?
I can try.
Yeah, go ahead. It's okay. Yeah.
Yeah. As previously I already said, that we already have the ML course and CV course, and I have some experience with simple model like CNN or detection models. And my thesis also about my ML stuff. It's in the area of self-driving cars. Currently, I'm working about prediction of traffic agents.
Of what?
Prediction of traffic agents of future trajectory of the traffic.
Okay.
For rankers.
Mm-hmm.
Yep, and from that course, I would like to learn about some more advanced stuff, like image segmentation or
Interesting, yeah.
something else. Yep.
Mm-hmm. Pretty nice, very nice. Anyone else?
Hi, my name is Muhammad.
Nice.
My bachelor was in mechanical engineering, and like Nastia and Sergey, I studied. I'm now a second year master's robotics, and I studied with Professor Khan, machine learning, and Professor Fahim, Muhammad Fahim, computer vision. My thesis topic is about defect detection using I'm trying to implement some computer vision algorithms for defect detection. So now, like, I hope I can learn more from this course so I can implement them in my thesis.
Nice. Can you tell me who are you doing your thesis with?
Now I'm like my supervisor is Ribi. But on papers, it's Professor Klemchik, but who supervises me really is Ribi.
Yeah, makes sense. Thanks a lot, Mohammed. That's an interesting background.
Thank you.
I'm going to try to like incorporate as many things about like self-driving cars as possible. Although like their data sets are usually too big to kind of do something interesting. But yeah, we can do something with that. So in the last versions of this course, I had a lot of students who are already working with self-driving cars. So their final project, they did it a lot about like, either self-driving cars or like those drones. So some of them did the landing for the emergency landing for drones. So basically they segment the different images that they get, and this is like a safe place to land on, or this is like a dangerous place such as a tree, so you cannot land there. And yeah, that was pretty interesting. Others, they did stuff on like self-driving cars for like lane detection and for the detection of other cars and human beings, pedestrians. So that's pretty interesting field, yeah. Anyone else? Go ahead, don't be shy. The first person on my list is Abdelaziz Sharawi.
Hello.
Hello there.
Yes, I'm Abdelaziz. I'm also second year master's robotics. Also, I have experience. I had the course with Professor Adel Khan, machine learning also, and computer vision. And my thesis is with Professor Igor Gavanov. It's concerned with the teleoperation of manipulators. So that's it.
And your bachelor's?
My bachelor's was mechatronics.
Mechatronics. Okay, cool.
Yeah.
Do you have experience with PyTorch and stuff?
Yes, I've worked with Python in my bachelor's. I worked on some projects of color detection and simple shape detection.
Cool.
And also in Professor Mohammed Fahim course, computer vision, I worked on a project that picking and placing of object detection of a pig and performing a pig in hole task using YOLO version, YOLO v5 actually. Yes.
YOLO v5, nice. So definitely on PyTorch, yeah. Makes sense.
Yes.
Very nice.
Yes.
Next person I think would be Al-Batul Yassin.
Hi, I'm also a second-year master student robotics. Like my colleagues, I had 2 courses, machine learning with Professor Khan and computer vision with Professor Fahim. So I have like quite experience with the things you mentioned and asked for. And I'm doing my thesis right now with Professor Kaponov in impedance control in teleoperation applications. That's all.
Cool, cool. And your bachelor's?
Mechatronics.
Mechatronics. I have no idea what mechatronics is, by the way.
It's like mechanics, electronics, and a lot of things to get. So
cool, very nice. So, well, thank you. The next person is Ayomid Bakar.
Yeah, good day. So you almost got the name right, but it is Ayomide Bakare.
Ayomide Bakare. Okay, nice.
Yeah. So I am master's second year data science student. I also have like some experience, as my colleagues have said already, in machine learning with Professor Khan, and right now I also have experience in front-end engineering. I have experience with a couple of programming languages like Python, Ruby, and the obvious ones. Yeah, so that's basically everything about me. I did my bachelor's in electronic and electrical engineering.
Ooh, nice, interesting.
Thank you.
Where are you from, by the way?
Nigeria.
Ah, from Nigeria. Nice. I had a lot of friends from Nigeria.
So I'm currently in Nigeria. Oh, awesome.
You're still in Nigeria right now, or did you already get to Innopolis?
Yes, I am.
Okay, nice.
Yeah, unfortunately, due to travel restrictions, I can't get to Innopolis yet.
Ah, yeah, makes sense. Yeah. Thanks, Bakari. Next person. Do you guys want to volunteer somebody, or should I continue from the list?
Can you hear me?
Yes.
Good evening, everybody. My name is Kichi. Second year master's student, robotics master's student.
Okay.
So my bachelor's was in mechanical engineering.
Yes.
Like my colleagues said earlier, I have experience with machine learning and computer vision, which we did under Professor Khan and Professor Fahim.
Cool, very nice. Just can you tell me how to pronounce your name, by the way?
Did you get that?
I did not hear you at all, sadly.
Pardon?
I think you're having like some internet connection problems.
My name is Ikechi.
Ikechi, nice to meet you. So can you tell me where are you from?
From Nigeria.
Ah, from Nigeria also, guys. Nice, that's very nice.
Thank you.
Thank you. I think next person would be Mikhail. So Micha, I already know you very well, but go ahead, present yourself to the others.
I'm second year master students for data science. I'm familiar with computer vision and I've taken course from Adil Khan. And right now I'm working with satellite imagery, like forest detection and field detection. So I'm very interested in object segmentation tasks and recent advances. So
cool. Did you take the course from Professor Fahim on computer vision?
I think so, yes.
Nice, very nice. Next person would be, I think we did a good job, yeah. We've seen Sergey. Sergey, did you present already?
Yeah, I can I can do it one more time if you want.
No, thank you. That's enough. Thanks a lot. So that's good to know, you guys. It's nice to get an idea of who are the people who are going to take this course. So for now, we can get started and go ahead and start the first lecture. So the first lecture is going to be something very easy, something you guys have already seen before, and I'm hoping that it wouldn't be too difficult for you. Or it shouldn't be new at all, actually. I think the break should be in like 1 hour, right? Yeah, cool. So if you guys need a break or anything, please tell me. We could take a break either right now for like 5 minutes, or we can take a break after at least like we go a couple of slides. Which one do you prefer?
Let's continue.
Let's continue. Very well.
Yep.
So the first lecture is going to be about image classifications with CNNs. So the content is going to be very easy and generic. I'm assuming you already are familiar with neural networks. And then we'll speak about convolutional neural networks, and then we'll speak about some tips for CNNs, right? So first part is going to be only about neural networks in general. So we will start speaking about what classification is, what regression is, basic stuff like this. We will speak about logistic regression, and then we will jump to things related to neural networks in general. So first, can you guys tell me what is regression and what is classification, right? Go on. I think there is like
Okay, yes. Classification is related to categorical data, while regression is related to real numbers.
I wasn't very much able to understand your answer. Can you please like type it? Anybody else wants to answer? Ikeshi, please type your answer.
I can try.
Yeah, go ahead, Sergey.
I think the main difference between the two classes is that classification is more about we trying to predict that some object belong to some certain class, and regression task is more about predict some continuous value.
Okay, so if I ask you, for example, is object detection a classification or regression task?
I think classification.
Okay. Does anybody else have like different opinions? Maybe definitely you guys have already seen what object classification is, right? What object detection, right, is. And you have already seen. Yeah.
I agree with Sergey. I think it's the classification task.
You agree with him? Nice. That's very nice.
Isn't it both? Like we decided the class and the like coordinates of bounding box. So it's both numbers and class. So it's both in classification and regression.
Well, that's a very good point of view. Who else agrees with Micha? Go ahead, guys. We are just discussing. We're trying to learn together. So there are no wrong answers, no right answers.
Can I give a counterpoint?
Yeah, of course. Go ahead.
I think for object detection, the prediction function that we're getting, the output of that is multi-class, right? We're not getting any sort of numerical value. It doesn't belong. It doesn't belong to like the set of real numbers. So I don't know how is it. Maybe I didn't understand his point, like about where real numbers play.
That's a good point of view. Nice. So basically, you're saying it's just a multi-class classification, right?
Yep. I mean the predictive function, that the output of that only belongs to. I mean it's a subset. I mean the elements belong only to like a finite set. So based on that only. Yeah.
Very nice. Anyone else has a different point of view? Since everybody has at least taken the course of Professor Fahim, and you have seen the different architectures. So you have seen YOLO, you have seen RCNNs, fast RCNNs, how they're working. So what do you think? Go ahead, guys. There are, again, no wrong answers. Usually Egyptians and Syrians give always the good and correct answers. So I have high expectations for you guys. Go ahead.
I think I agree with that. It's both classification and regression. Classification, nice. When we try to detect which class it belongs, and regression if we want also to detect its locational position in the framework.
Very well, thank you. Does anyone else have maybe a different point of view, or like wants to agree on something that has already been said? Okay, very well. So I agree. Thank you, Ekechi. So you agree that it's a pure classification task. So I think the most correct answer is the one from Micha. So yes, it is a classification and regression task. So basically, the object of object detection is to find the location of an object inside a big image, plus to categorize this object. So the categorization or classification part is easy. So this is a $sign, meaning this is a classification task. So we have the classification part easy. Now for the regression task, the output of all object detection models is going to be coordinates, right? So either you're going to be working with this kind of coordinates plus width and height. So basically you will have the coordinate for the X and the coordinate for the Y, meaning you're going to have a float number. Usually this number is between 0 and 1, or between 0 and well, the width of the image, right? So well, we will be mostly working with this kind of implementation. So between 0 and 1, meaning you can get any value between, like, for example, 0.2, 0.3, 0.33, for so on. So here, the first part of classification, we said it's here. The second part of regression, which is basically detecting the width, the height, and the different coordinates of the object. And all of these four values are completely float values. They're real number values that usually tend to range between 0 and 1. So basically any value between 0 and 1 is admissible. Hence, the classification and regression are both used inside. Yeah, go ahead, Micha.
I heard something about like pixel by pixel classification, like you're going from like during like using windows or exactly for what each pixel you predict in the class. Is it more close to segmentation, or it's something like old algorithms that I'm remembering?
You're speaking about both. So basically what you have just described is the first model for object detection that we will see together. We will create or like make the logic for this model together during the lecture. But it also could be something called as, I don't want to use it's always something difficult. So pneumatic something, what is it called? Let's Google it. Sorry. Let's go to Detectron 2. So it's a segmentation task, but I forgot the name of this segmentation task. We can find it in projects. Can you see the word projects? There it is. No. They remove it? Ah, this is Detectron 1. Okay, Detectron 2. There it is. Projects. Can you find some weird word that starts with, yeah, there it is. Panoptic segmentation. So this is the algorithm that you just described.
Thanks. Yeah.
You're welcome. Where is the lecture now? Yeah, image classification. Present. Okay. Let's go back. So now that we understand kind of the relationship or what is classification, what is regression, I'm going to ask you a very simple question, and I'm sure that all of you guys know the answer already. Are these two types supervised, unsupervised, or what exactly? Go ahead, Michaya. Answer without raising your hand.
I just want, it's both supervised. Yeah, everybody knows.
Very well. Does everybody know that? So if I ask you a simple question, right? I'm sure you're all familiar with GANs. Are GANs a supervised or unsupervised technique? Go ahead, answer everybody. Again, there are no wrong answers, huh?
They are unsupervised because they use the same input data without labels.
Yes, so they are like unsupervised in their more like generic format, right? So normal GANs are completely unsupervised. Now let me ask you a question. What is this part, the second part of the GAN? Go ahead, guys. Yeah.
Discriminator.
Nice. Discriminator. Does the discriminator use something very similar to classification?
Yes.
Nice. Now let's go to the unsupervised part. Again, let's go for something else. Like, I'm very good at drawing, but so there you go. So what are these?
Encoders.
Autoencoders, very well. So autoencoders are again a type of unsupervised learning, right? Can you tell me what do they actually do? Yeah, go ahead, Michael.
They reduce dimensionality of image during the encoding.
Yes.
Like creating the internal representation of that concept or image, and
Nice.
trying to restore it during the up convolutions. I don't
Nice.
remember the
decoding
during the
part.
decoding. Yeah. Process.
Now, can you tell me what is actually decoding, right? Isn't decoding just a fancy regression? Every pixel you are trying to decode is just a value for regression, right? So in reality, what you are doing is you are just finding different regression values, right? Similarly to object detection, where you are doing regression only on 4 values. In this case, you are doing regression on the whole image. So you see, yeah, go ahead.
Sorry, I'm not that familiar with autoencoders. Is it while this decoding thing is happening, it's is it doing some sort of principal component analysis, like getting?
It's too complicated, right? Going to principal component analysis is a bit too advanced, right? We're very basic here. Imagine this is this is a picture, right? It goes through a neural network. Don't care about the shape of the neural network. Does it have like fully connected layers or convolutional layers? Imagine it's the simplest neural networks you're already familiar with. The input is the image. The output is the exact same image. This is autoencoders. Okay?
Okay.
So they're very basic architectures. They give you the same input you gave them, right? Of course, depending on the architecture, they give different tasks. They do, or they can be used in different situations, but their main principle is this. They take an X, they give you back something similar to X. But what they are doing in reality is just regression, right? So there's nothing fancier than that. So basically, like previously, when we when machine learning started and data science started, classification and regression were both tasks only used for supervised learning, and then other tasks such as like clustering and dimensionality reduction, they were for unsupervised learning. But now, with more innovations and newer techniques coming up every day, we can see classification and regression happening in unsupervised learning, and we can see a lot of unsupervised learning techniques used in supervised learning settings, right? So definitely try to keep an open mind. There is nothing that can constrain regression to stay always in supervised and constrain classification to stay always in supervised. Yeah. So that's good. So that's nice. We are already familiar with what supervised is, what unsupervised is, what regression is, what classification is. That's nice. Now let's speak about the first algorithm that everybody has studied in machine learning, which is linear regression. Just to confirm, for the person who who is just starting in their first year of master's, did you already take the course? Did you already take the linear regression lecture with Professor Khan?
That's coming next week, actually.
Ooh.
But yeah, but I'm familiar with linear regression.
Yeah, you're going to have a lot of spoilers in this lecture, guys.
Okay.
That's nice. So what linear regression is, it's a very simple model. What it does is it tries to convert a concept to a different one. How does it do that? So for example, we can convert the concept of a weight into the concept of height using just a simple linear formula. So I'm sure you have already taken some linear algebra or did some math in your high school. So you should know what is like this, right? What this is.
Yeah, just to mention, like if you're taking it to like higher dimensions, it's just W transpose times the feature thing plus some B is like the value at 0, like.
Yeah, some bias. Well, we don't take things into higher dimensions in this course. Like we keep things in the most simpler forms as possible, right? I'm also very bad at math, so take it easy on me. So here, this is like the most basic formula for linear regression that everybody knows. We have an input concept. I try to emphasize the word concept here. So we have an input concept, which is X. It's a real value that represents the weight, or yeah, the weight in this case. And we can map this concept into another one called height, right? Using just a simple formula like this one. And our goal is to learn these A and B, which kind of give us the lowest error possible, right? So this is what linear regression is trying to do. So first thing, is this like a regression task or a classification task?
Regression, right?
Nice, very nice. And do you know what are the algorithms used to find the values for A and B?
You do linear least squares for some, I mean, yeah, linear least square works, but I don't know any other algorithm, like better algorithm.
Well, there is like a worse algorithm called what is it called? This gradient descent, right? So you could use gradient descent on this one, spend a couple of hours doing it.
Oh, gradient descent is the one where you go negative of the gradient descent, like slope.
Yeah.
I mean, yeah. Okay,
That's
gradient
right.
vector. Okay.
Yep. So basically you take something like this and you follow this vector, right? You keep on improving the loss function. That's very nice. Now, can you guys tell me why we cannot use linear regression for classification? It's a very powerful concept that can map like a concept. It's a very powerful algorithm that can map a concept from one space to another, which is pretty useful. But why can't we use it for classification? Anyone knows?
We can if we set a boundary, right? If something is less than something, then it is something, and if it's more than that, it's something else. That can work, right?
Amazing answer. I really like this answer. Can somebody tell me something else?
It's harder to build the loss function. Like when you have labels just like 0 and 1s, and you're trying to get the difference of your predictions, they're like not really easy. We need to modify the loss function for it to work.
Okay, nice. Anyone else has any other issues with linear regression for classification? Or in other terms, why did we invent logistic regression if we already have linear regression, right? If we already have this algorithm which can map linear regression to a classification, why did we bother and go for logistic regression? What is the bonus that we get with logistic regression?
Yeah, you cannot take a derivative of if statement.
That's a good one. Yes, we cannot take a derivative of an if statement. Anyone else?
I think the main purpose of logistic regression is to apply, to use nonlinearity in our model. If there are any nonlinear dependence from input and output.
That's a very, very, very good answer, but we will discuss it a bit later on. So just a small, we will speak about it when we get to logistic regression. So let's put it here, non-linearity, with a couple of question marks. Nice. So another one. What happens if I give you y equals 5x plus 10, and for some reason, x equals 1 billion? Can you tell me what y is? Right. Can somebody tell me if this is easily interpretable by you, right? So if I tell you class 1 means person is safe for, what is it called? Lending money to. Class 0, person not safe. What does 5 billion mean to you? How can you interpret it?
I don't know if you saw it.
I'm thinking this was Ikishi. Yeah, just try to send your answer in like the chat. Very nice. Anyone else? Can somebody tell me what is the problem in a response such as y equals 5 billion and y equals minus 5 billion compared to a response like 1.5? I have typed it already. Oh, okay. The data format strings is not suitable for linear regression. That is true. We need to convert it into an integer or a float. But this problem is the same thing for logistic regression, right? So if you are already familiar with logistic regression, then you know it's just like a linear regression, but with a little bit extra steps, right? So again, string values cannot be inputted to logistic regression directly. So that's not the problem that we have created logistic regression for. Mainly the problem is a question of interpretability, right? So if I tell you the y or the prediction for this client is 5 billion and the prediction for that client is 3 billion, that's not going to simplify your, what is it called, interpretation of what the model is saying. But if I tell you always the results are going to be between 0 and 1, something such as 0.99 means the person is very safe, but something like 0.7 means the person is not very, very safe, right? So he is safe, but not very much. But when it comes to an unlimited or an unconstrained value, you can never really tell. Is 1.06 or 1.09 safe enough? Or is 5 billion safe enough, right? So when you don't have any constraint to what the predictions might be, you cannot really interpret it as like a comparison method for your classes per sample, right? So basically, you do not have this concept of comparing the different samples. But when you have something that is always between 0 and 1, so it's a constrained output, you can easily interpret it as a probability, and from then on, build different applications on top of it. So the only difference between logistic regression and linear regression is that logistic regression equals linear regression plus constraint plus if statement equals decision plus probability. So again, this is what happened. This is how we created logistic regression. We took linear regression, we forced it to become between 0 and 1. We added a small if statement on top of that, and that gave us the decision or the classification plus a very important concept, which is the probability. Now, let me ask you a small question, and anybody can take, can basically start annotating. I think anybody can. Can you draw, in this case, where the decision boundary is? So if I tell you that if statement, there it is. This is it. So anything that is higher than 0.5 means it is class 1. Anything lower than 0.5 means it is class 0. Can you draw the decision boundary of this model? Go ahead. Huh? I think you guys can draw on my screen, so go for it.
I don't think I can draw on your screen.
Okay, so if you cannot draw on the screen, I'm not sure why, but let me try to enable it first. Can you try now? Annotate. Do you guys have this annotate button that you can press on?
Yes, I do.
Okay, so try to annotate on my screen. Yeah, nice. Micha was able to do it very well. Go for it. Anybody can try to annotate the decision boundary in this case. First, is the decision boundary this red line? Anybody can answer, huh? Don't worry. Please open your mics and answer through the mic or through the chat. No need to ask or ask permission.
Are we looking for like results of our function, or we are looking at data?
Nope, I'm looking for something called as the decision boundary.
So we need to graphic of our data. There we can draw it.
I cannot answer you or like help you with this one. I need something called as the decision boundary. I want to see if you guys already know what is the decision boundary. How does it look like?
What if the value is exactly 0.5? What happens then?
Yeah, here is something. Is this the decision boundary? Do some voting, right? Tell me if yes or no. Or is this the decision boundary? You think so? Thank you, Ikichi. Anyone else? Please do participate. Give your opinions. This is how you guys can learn.
I think the first option is correct.
You think the first option is correct? Very nice.
Red line.
Red one. Okay. Anyone else agrees with the red line? Just so I could give you what is the decision boundary. A decision boundary is something that splits, or it's the, something that does this. Class 1, class 2. So this is in like higher dimensionality. Yeah, so this is in like higher dimensionality. This one is the decision boundary. Can you guys tell me what does the decision boundary look like for logistic regression? Huh? Red one should be the red one, should be the red one. Okay, nice. Now let me give you maybe a different answer and you guys can tell me what you think. What about this one? The green line. Is this one the line that separates the two of them? So depending on your answer, of course, the red line is a linear line. This one is also a linear line. but the green one is a nonlinear line. So do we have a nonlinear decision boundary for logistic regression? Or is it a linear decision boundary? The decision boundary is what defines if a model is linear or not, right? So if I say this is a linear model must have a linear decision boundary. If I say this is a nonlinear model, then it must have a nonlinear decision boundary. Still think it's the red one, very well. So nobody thinks it's this green one. That's a very good start. So the green one is completely false. The green one is a nonlinear line, and a nonlinear line can never give you a linear decision boundary. The correct answer is this. Here. So this is the decision boundary for logistic regression. So again, what it gives you is everything from this side is predicted as positive class. Everything from this side is predicted as negative class. So basically all of these samples are correctly classified. Sorry. All of these samples are correctly classified. These 3 samples are mistakes. These 2 samples are mistakes. And all of these are correctly classified. Did you guys get it? Nice. So do you understand what is the decision boundary and why is it here exactly? Because the decision boundary splits the data, right? So the data is your X. This is the Y. We don't care about what Y is. We want something that splits the X axis. So basically the decision boundary is this point. This is the decision boundary. So basically during the quizzes and in the midterm exam, questions are going to be similar to this one, right? So for example, I would give you something like this. I would ask you something like this. What is the decision boundary? And what is its formula, right? So in that case, what you would do is you would put in the formula of this S-shaped line, find its intersection with Y, and then find the X that gives you the intersection with 0.5, right? So basically you say Y equals 0.5, replace the formula of Y and solve this equation. And then it gives you X equals, in this case, I don't know, 0.23 or something like that. So this is what you should expect to have in your quizzes and in your midterms. Now for the final part of logistic regression that we will discuss. What is this function? What is this function that maps a linear regression into a probability? I'm sure all of you know it, right? Sigmoid, very well, sigmoid, nice. So this is sigmoid. Can someone tell me what's like important about sigmoid? What are the 2 things that are like most important about sigmoid? Sorry. Bounded between 0 and 1. This is yes, differentiable and bounded between 0 and 1. These are the 2 most important things, and this is the reason why we chose this function, or the sigmoid function, on top of a logistic regression to give us this fancy logistic regression part. Nice. So I think we can take a 5-minute break, 5 minutes break right now. And yeah, come back in 5:05, and we will continue our sweet lecture. Okay?
Yeah, thank you.
You're welcome. Resume. Very well. So I see that we have written a very good part of the resume. We will come back to the lecture notes in a couple of minutes or a couple of something. But for now, let's go to the other part, right? Let's finish the lecture. Let's close all this, close this, close this, close this, close this. Insert, close this too. And go ahead with our lecture. Here we go. Can you guys see the screen again?
Yep.
Nice. So this is where we stopped last time. We spoke about logistic regression. We've seen what it is. We've seen that it's just linear regression. We added to it a sigmoid function so that it becomes more interpretable, gives you results between 0 and 1, and such that it's more, how do we say, it's more differentiable, meaning it could be used in a bigger setting that requires a little bit more calculations, right? Something that could use derivatives. Now, let's keep this in mind and keep in mind that logistic regressions is a linear model, but it does use a nonlinear activation function. Let's see why and what is the importance of this. So remember, your friend said we use logistic regression because it's nonlinear. It's a bit of a wrong answer, but it's a very good wrong answer. So it's a highly appreciated wrong answer. From this concept of logistic regression, somebody tried to change this concept and call it something else. So somebody tried to call this concept of logistic regression and call it perceptron. Same thing, same values, same calculation, same everything, but different name, right? So if you already understand what logistic regression is, you should already understand what perceptron is. So perceptron is the first type or the first emission or the first try of neural networks. So basically it is single layer, single node neural network. It consists of 5 main parts. So the first one is the input. The input to a perceptron or to a normal neural network in general must always be a vector of real values, right? So it does not work with strings. It does not work with images by default. It does not work with anything else besides vectors of real values. The second part is the weights. So the weights or the weights and the bias are what was previously called in our function the A and B, right? So this is the A and B of your logistic regression and your linear regression. The second part is the summation. Of course, in linear regression, we also do the same thing. So we multiply the inputs with the weights, and then we sum everything together. And from there, we send them through an activation function. In our case, it was the sigmoid function, right? So this is what perceptron is, and this is how it relates to logistic regression. A multi-layer perceptron now is kind of the generic neural network that you would see nowadays. So what it does, it's just stacking those perceptrons, thousands of those on top of each other. Let's say we stack 100 in the first layer, and then we stack another 100 in the next layer. So basically what we do is we have logistic regression. Here it is. Instead of performing one logistic regression on the input, we perform 100 logistic regression. And then we use the output of these logistic regressions as input for another logistic regression, right? And this is what's happening in neural networks. So basically, it's a logistic regression that is sending its output to different logistic regression that is sending its output to different logistic regressions. And this is why I was emphasizing the fact that linear regression and logistic regression, gives you a very specific or special ability of mapping from one concept to another. Remember, one simple logistic linear regression allowed us to go from weight into height, right? So mapping from one concept to another with just one node. We have this big map. Now imagine if we can do this mapping multiples and multiple of times. So basically we have here, this one is calculating, let's say, height. This one is trying to figure out the gender. This one is trying to figure out the age, different things. And then all of these things are being mapped into other concepts, other more complicated concepts. So let's say this one is trying to figure out whether this is a carnivore or this is a herbivore, right? So does it eat meat or does it eat herbs, arbors? I forgot the name. Green stuff, those trees, right? So does it eat meat or does it eat trees? So this is what's happening in neural networks. We're building different concepts and then we're mapping them into a more complicated concept. And we continue this complication of the concepts further on until we arrive to the final layer where we find our target concept, right? So for example, here we start from stuff such as age and height. And here we go to something like, is it a cat or a dog, right? So we're mapping from one concept, from multiple concepts to another concept, but now we're doing multiple intermediate mappings of concepts, right? So we're trying to understand more deeper our data, right? So this is the power of neural networks. This is why they're very useful. Again, we have seen that one of these small nodes can do a very big job of understanding or mapping from one concept to another. Imagine now this one concept being mapped multiples and multiples and multiple times. And instead of being one concept, now imagine it being hundreds of concepts being mapped and combined multiple times. So this allows you a more deeper understanding of the data and definitely gives you a better chance of understanding and giving better performance on the data.
I have one question.
Yes, go ahead. Yeah.
Yeah, so in the different layers, it's showing the input vectors are of different dimension. Am I correct? Like one layer to the other, like it's showing
yes,
belong to RS, RW, something, right? Different dimensions,
yes,
basically.
Different dimensions, yes.
So it's kind of removing features or adding more features, sort of. Like, is it like those
It's
numbers
not,
RN, RW, is it increasing or is it decreasing or doesn't necessarily follow any order?
necessarily nothing is happening, right? So what's happening is you have 100 concepts in the input. They get mapped into, let's say, 50 different concepts. Did these concepts like remove or did they add? They didn't remove, they didn't add, they completely replaced, right? And then we map them into 20 different concepts. But these concepts are more higher level, right? So for example, here we had a concept such as age. Here we have a concept such as, is it a, does it eat meat? Meat or vegetarian, right? So here we have a higher level concept. And then maybe it will map these 20 concepts into 100 different concepts. So the size doesn't really matter, right? We can go from 100 to 50 to 20. You can go as much as you want, right? Okay. So we're not replacing, we're not removing or adding new. We are completely replacing them and mapping them into a different set, right? Each one of these 100 concepts is being mapped to one concept in this 50 layer, right? So 100 concepts become
meaning the nodes, right?
Can you repeat this?
By concepts, you mean these nodes, right?
Yes. A concept is a node or a value. A concept is just one real value, right? Such as the height, the width. It's just one value, right?
Okay,
so all of these 100 concepts are being used to calculate one concept such as height. Here it is. And then the same 100 are being used to calculate another concept such as the width, let's say. We repeat this operation 50 times in the first layer. If we repeat it 50 times, that means we get 50 different concepts. Remember, each one of these nodes is a logistic regression on its own, right? Meaning it is taking all of this as input, each one of these taking all of this as input and mapping it into something new. Okay?
I'm still a bit confused though. I mean,
Go ahead.
one node has multiple parameters and taking that input vector, right, and doing something to it. Correct?
All of them, yes, all of them are the same like this. All of them take their inputs, the different inputs, and multiply it with their own weights.
Okay.
So every single node that you have seen in that blue thing looks exactly like this.
One node is this whole like thing, architecture.
Yes. So you see this node looks like that old architecture. This node also the same thing. This node does exactly also that same thing.
Okay, I see.
Okay.
I see. Got it. Thank you.
You're welcome. Just to confirm, you are the person who is like first year student, right?
Yes. It's obvious.
It's gonna be a bit it's gonna be a bit difficult for you during this course, but do your best to follow up and of course ask a lot of questions and interrupt me during the lecture. You're always welcome. Okay.
Sure. Thank you.
Nice. Yes. So again, for example, this input layer will take the input. We'll take your input or the real input. It will take your data set as input. But this second layer, it will not take your data set as input. It will take the output of this layer, meaning it will take the different outputs of every single one of these logistic regressions. Okay? So here we have the data. Here we have the logistic regression set 1. This is the output that is being sent as input to this one. And here we have the output of logistic regression 2 that is sent into this one. Okay? Okay. Nice. So just a couple of remarks that I would like to confirm with you guys before we go to the next part. So the bigger and the wider the neural network is, the better the more chances it has of giving a very good performance, and the more chances it has of learning the data, right? Of understanding the data better. But this means that it risks a lot falling in the overfitting category. Now, overfitting is a concept that I'm sure you have not studied yet, right?
I'm aware of overfitting. Yeah.
You already did this, right?
Yeah, we did it in the first lecture. Yeah.
Okay, so yes. So if you have a very big and very strong model, this means this model can overfit very quickly, right?
Mm-hmm.
Nice, very nice. Then yeah, exactly. If you understand this, then that's amazing, right? And the second part is that neural networks are trained using an algorithm called like an optimizer. And basically what it does is that it will reduce the loss function by changing the different weights of the neural network. So these are the different weights of every single node. Now we have, let's say, 200 nodes, 200 weights for each one of these blue dots, right? So 200 multiplied by 100 plus like 200 multiplied. So it's going to be like a lot of weights, right? So we're trying to learn millions of different numbers that will give us the best neural network possible. I will not go into more detail in this one because we will spend a lot of time on it, but just this is like an overview of what neural networks are. Now, a small question for those who are a bit advanced. And it's basically related to the remark of your friend who said that the activation function was used to introduce nonlinearity. If we use a neural network without any activation functions, is it going to have a linear decision boundary or a non-linear decision boundary? Now imagine in this setting, our neural network contains hundreds of layers and hundreds of nodes in every layer. It should have a linear decision boundary. Very good. Anyone else? Don't be shy, guys. Give me your opinions. You agree. Very well. So let's just give it a small proof. Let's put two linear regressions on top of each other and see what happens, right? So you say y2 equals a2 times y1 plus b2, and y1 equals a1 times x plus b. So the proof that we are trying to find is is y2 equal to some big A times x plus some big B, right? So we're trying to find out if y2 is a linear function of x. And we can do that very simply by doing the following, right? So y2 equals a2 multiplied by ax plus b plus b2, which is equal to a multiplied with a2 multiplied by x plus a2 multiplied by b plus b2, which is equal to a multiplied by a2. So this is our first term, x plus our second term, which is this one. And there you go. We managed to find that y2 is a linear function of x, meaning a combination of two linear regressions without any activation function always gives you a simple linear regression. Now, using the, like, what is it called? Recursive, proof. I forgot how to say it in English, but proving with recursion, right? You can prove the thing that we have just said about neural networks being a linear model. Yes, it's just a composition of linear function by induction. Yeah, thanks a lot. Thank you. Sadly, since I'm studying only in French, so it's the English words can be a bit difficult for me to remember. Very well. So again, remember this proof because this could be like this is very likely to be the type of questions you will get during your exams, right? So I'm just trying to prepare you guys for how your exams will look like. Now, how do we fix this problem, right? So we just said that neural networks are linear functions if we stack them as just linear functions. How can we fix this problem and introduce the non-linearity, right? Can somebody explain to me how activation functions give you this non-linearity and how does that improve the kind of concepts that we can learn? Or what are the different activation functions that you guys know?
No, like hyperbolic tangent, tanh,
Yes, tanh,
and
nice.
Rectified linear unit.
Nice. What else? ReLU, very well, nice. Can somebody tell me, is ReLU better than tanh? Why and how? Aha. Which one is better for what? Why don't we use polynomials? They're also differentiable. So this, but it won't be bounded. Yeah, that's a very good question. And we can definitely use polynomials. Yeah, we certainly do. There is an algorithm called polynomial linear regression, right? Why don't we use polynomials, right? It's just too complicated, right? So you get this very big calculation. Probably just didn't give good results. Or maybe because it suffers more from a, yeah, that's a good question. Yeah, let's speak about this. Why polynomials are bad? Simply, if you have like values which are already big, polynomials are going to be huge. If you have values that are like kind of small, polynomials will get even smaller, right? So this small getting smaller, big getting bigger is a big problem for neural networks. I think learning rate will play a role here. Yeah. So this this problem of small getting smaller, big getting bigger leads to two very big problems, which are exploding gradients and vanishing gradients. In both cases, your neural network will start giving you NaN, so not a number errors, or will give you 0, 0, 0, 0, 0, 0, 0. So this is why polynomials are kind of bad as an activation function as their own, on their own, right? But very good question, yeah. Anyone else can tell me why tanh that looks like this, right? And this is the 0. Is why is it different from rectified linear unit? What are the differences between them in terms of speed, for example? Which one is faster during training?
As far as I know, ReLU is better choice for that.
For what? For training or quality of non-linearity?
For training?
Yeah, in terms of time, speed, or in terms of quality of training?
ReLU is obviously non-linear. No?
Yes, it's non-linear, but is it faster than tanh?
I don't know.
Think about it. Tanh is a very, very complicated function, right? Its derivative is also a very complicated function. So doing gradient descent with a very complicated derivative takes a lot of time. Doing gradient descent with a simple derivative of the same value is much easier. Which one do you think is easier? So I'm assuming you guys have already studied all of these concepts, right? So right now we're just doing like a kind of a revision on what you guys have already seen. Of course, everybody besides Randall, who's new. But yeah, so overall, ReLU is much, much, much faster in training than all the other activation functions. And tanh is very useful in specific situations, right? So for example, if you're trying to find a value that must be between -1 and 1, tan h is your answer. But if you're trying to find something that is just a good activation function for linear, for neural networks in general, then ReLU is definitely your best choice. We can speak a bit about why tan h is a very good one for specific cases and not very good one for the general case, maybe after we finish the lecture, right? But I think can be expressed as some sort of exponential, so derivative shouldn't be a problem. I didn't really get your answer. Maybe I forgot what the question was. But yes, tan h again is a complicated function, meaning its derivative is going to be also a complicated function, meaning its calculation is going to take time. Whereas something as simple as, what is it called? As ReLU, its derivative is basically number 1 or number 0. So the easiest thing you could ever calculate and the easiest multiplication you will ever make, meaning the calculations of gradient descent and the training of the neural network will go very, very smooth when done with, what is it called? Sorry, when done with tan h, when done with ReLU compared with to tan h. I think this is it, yes. So far during this lecture, what we have seen is linear regression, logistic regression, perceptron, and multi-layer perceptron. Now I'm just gonna go to that, I'm sure you guys have already done this before, the TensorFlow playground, and just take a look at it. This is definitely not gonna be useful for the students of the second year, but it's gonna be useful for the first year student. Yeah. So this is the TensorFlow, what is it called? The TensorFlow playground. For some reason. So here you go, you have a data. First, please, for the first year student, can you activate your mic and answer some questions? Is this data linearly separable?
No, no.
Why? Because
I can't really draw a linear function or a line which will like, I mean, if you're, yeah, I mean, if blue is different and orange is different, then we can't really draw a straight line.
Yes. So this, you see this decision boundary, the one in white?
Yeah.
This is what the neural network has learned, right? So we used an activation function of tan h, and this is what the neural network has learned. So you see, this is a neural network of a variant size, as you can see. Now let's try to do a bit something more, right? Let's try a linear model, right? So this is a model, a neural network, same size, same everything, but with a linear activation function, meaning there is no activation function. So there you can see it did not learn, right? So it's not learning anything that is useful because it's unable to learn anything useful. Now let's try to add some nonlinear features. It was able to work with it, right? So these are nonlinear pre-processing techniques that we have added. And when we added them, even the linear model was able to give us a nonlinear decision boundary. So this is a very important technique that you could take a look at. I'm sure you will study it later on with Professor Khan, but for now you have just seen how does adding nonlinear input give you a nonlinear decision boundary. So let's see, this is what happened? For some reason, it's not learning, or it's not giving good results. Okay, it's learning. Yeah. So there is the output of ReLU. So you see, it's definitely non-linear, but it's composed of different linear parts, right? So it's not as smooth as tan h, for example. Can you see it?
Yep.
Let's take a look at, for example, how sigmoid would give us. Let's try to increase. Yeah, there it is. Okay, so you see, sigmoid is a bit similar to tonnage. Let's go back to tonnage. Yeah. The learning rate is a bit too big, but anyway, let's take a look, for example, at this one with tonnage. Let's see if we can do it. Do you think the neural network can easily separate these two? Yes, it can if we add a little bit more. So this is the shape of the neural network that we are working with. So as we said, a bigger neural network has better chances in learning the data than a smaller neural network.
Can you explain what is that images on the graph means?
These images?
Yep.
Yeah, this is the output of the first logistic regression, remember? So this one, in reality, is just a logistic regression, right? Remember. Hello, the person who asked the question.
Yeah, I understand, but I not really get it, I think.
Simple. Yeah,
this
remember,
is
this is
decision boundary of this specific logistic regression.
Yes.
Like if we throw everything away and put our data, it will draw this decision boundary.
Exactly. So basically, if we ignore that this is part of a big neural network, if we look at it as just one single, what's it called? As one single, help me out here. Logistic regression, this is what it's going to give you. Sorry, let's go back. This is what it is going to give you. You see? But if we combine this with this, with this, with this, we would get something a bit more complicated. You see? You see?
Yeah, now I see.
Now we combine all these new things, which are a bit more complicated, into something even further complicated, right? And then we do it again and again until we reach something better. Of course, with a bit more time, it will definitely be able to find all of these.
This is overfit, correct? This overfitted network was.
Yeah, of course, it's definitely going to overfit, but it's going to get there someday, right? So overfitting is always, okay. Ratio of training to testing data. Yeah, let's give it more training data, zero noise. Make it bigger, nice. Let's see if it trains fast enough with ReLU. Yeah, there you go. Definitely a lot much faster than tonnage, right? So it did it in like 200 epochs. Let's see tonnage, how much time does it take? Tonnage is also looking good. Yeah, it's definitely looking good. In terms of number of epochs, it's slower than ReLU, but it's still looking good, right? Yeah, definitely going to be slower than ReLU. And every single epoch of tonnage takes more time than an epoch in what's it called? In ReLU. So for now, let's go back to our lecture notes and finish writing the lecture notes, right? So add the new section about neural networks in here, and then we take a 5 minutes break, and then we come back for the CNN parts. So you guys can see the lecture notes? Yep, go ahead. Somebody starts writing something very quick about perceptron, and then somebody goes about writing something about neural networks, right? On Sunday, Saturday morning. It's a bit late here in India. It's okay for everyone. Oh, yeah, it's true. What time is it for you in India?
It's almost 11. Oh.
Yeah, it's almost 11. That's a bit late. We're gonna finish very soon, okay? We're gonna finish very soon. Sadly, I don't think we could like make it a bit earlier because yeah.
That's okay. Like just for these 2 weeks, when I get to Innopolis, it should be okay.
Yeah, exactly. So hopefully it will be okay once you get to Innopolis.
Yeah.
Yeah. Sadly, I'm also working during the day, so of course with Pepsi. So this is why like this is the best time for me, and because of other courses with Innopolis, so it's a bit more complicated to get it in the morning. So yeah, go ahead. Somebody tries to write something for perceptron, and someone else tries to write something for neural networks, and then again we take our 5 minutes break and come back to finish the CNN part. The labs will be, of course, next week, so no worries.
Oh, okay, then that's fine.
Yeah, we're not going to have like 3 more hours of labs, don't worry. Nice. Yeah, just write about linearity, what it is. So stacking layers, write about linearity / non-linearity. Write about stuff about ReLU versus tonnage. And yeah, I think this should be enough. If Rondell is here, please write about, for example, their neural networks and the overfitting.
Yeah, I'm writing the neural net part.
Ah, very nice. So let's see. A single model that takes few inputs, multiply it on some weights, and then return a single value. Let's add just a smaller mark, very similarly to a logistic regression. A neural network that combines multiple layers of perceptrons. At each perceptron takes an input and outputs it to another perceptron, another set of perceptrons. Nice. These perceptrons / nodes can be complete graph depending on the rules we want. The more wide the layer gets, the better performance we achieve. Nice, but we also risk overfitting. Same thing for the depth. Same thing for the depth. And the same for the depth of the neural network. Very well. Linear activation function will lead to linear decision boundary because the combination. Very well. Value sort of linear function. So it's not, yeah, it's sort of a linear activation function, but it is definitely not linear activation. It's just sort of, right? Which performs in a faster manner due its simplicity for finding its derivative. Nice. Nice. Very, very good. Tan H is a complex nonlinear activation function which has complexity. So it's, yeah, very well. I think we're good for now. We're definitely good on the this part. So we will take a small 5-minute break, come back in at so for you guys it's 8. Yeah, come back at 8:25 and we continue our lecture. See you guys. Let's resume. If we do not finish the whole lecture today, then we can finish it. So so far our linear regression, we have seen what logistic regression is. We have seen perceptrons that we just linear regression, and then we spoke about multi-layer perceptrons. Now let's take the next step toward building a image classification neural network, which is a convolutional neural network slash combined with a multi-layer perceptron in. Convolutional neural, okay. This is breaking a lot. Is this something that everybody is noticing?
Yes, I'm busy with your.
Yeah. Okay. Sorry guys, let me ask. Oh, can you guys hear me now?
Yes,
Is it better?
Yeah, better.
Yes.
Let me test it. Okay, looks kind of nice. Looks nice. Perfect, nice. Something is broken. Yeah, probably my laptop is a bit screaming at. So let's just repeat this a bit further. So what we have seen so far is linear regression, logistic regression, perceptrons, which are just another form of logistic regression, and multi-layer perceptrons. Now, the second part of the lecture will be about convolutional neural networks, the 2D part for now. So convolutional neural networks are just simple feed-forward neural networks that use the convolution operation. So we will see this in more detail, but in reality, they are very basic modules. So first we will speak about convolutional neural networks in general, then we will speak about the dimensions of the output of the convolutional neural network, and then we will speak about pooling, and then we will, for now, let's watch this beautiful video. Can you guys see the screen?
Yeah.
Very well. I find this video to be a very, very fast one. So let's, yeah, but it's a very good one. There is no audio, by the way. So this is the input image, right? So you see there are lots of pixels in the input image. Every single one of these pixels is either, well, has a value, right? So it's a real value between 0 to 255. Notice what we are going to do is we are going to put a small rectangle called a kernel on the top of the list, like this point, and then we will slide it forward. This kernel, what it's going to do is basically calculate simple logistic regression, but only at this part, right? So remember what logistic regression does. So it takes the inputs, multiplies the input with some values, and then does the summation. Exactly what's going to happen here is the same thing. So basically, we're going to be applying logistic regression on different parts of the image. So here we see the logistic regression applied on this part. Then we move it. And as we are moving, we are applying logistic regression and calculating the output for logistic regression again and again. Yes, it's basic element-wise multiplication plus summation. It's just going through the different pixels 9 by 9 and then multiplying them with some specific values that it will learn. The values remain the same for all the image, right? So the same values that were used to calculate this logistic regression will be used to calculate the logistic regression in here, right? So it's the same logistic regression being applied everywhere. There you go. So here it is. It's calculating the logistic regression for all of these values, for all of these different parts of the image. So this was the output of one logistic regression. Now let's apply a second logistic regression. So here, this is a different set of values. So this is a second kernel that is going to be used or going to calculate a different logistic regression output, right? So imagine this was one node. This is a second node. Definitely a different type of output than what we have seen before. Nice. So what happened is in the first picture, right, this was the input. We calculated, let's say, 10 different logistic regressions, meaning from this one input image, we made 10 different images. After that, we stack them together and calculate the new images, right? Using, again, logistic regression, right? So this is the output of a certain logistic regression. This is the output of a second logistic regression. And then we repeat this operation again and again. Until we arrive to the final layer where we combine all the search space and basically say if it's a A, B, C, D, or an E. Sorry. Tuck. Yes. So this is, you guys can see the screen?
Yeah.
Nice. So just to confirm, everybody besides Randall has already seen logistic convolutional neural networks in detail, right?
Yeah.
Nice. So let's apply logistic regression on this input image, right? So basically, this is the weights of a certain logistic regression kernel, right? Of a convolutional neural network kernel, which is just logistic regression, remember? And what it's going to do, this is the input image. Can you please calculate the multiplication or the output of this kernel? This is mainly for Randall. Huh? Hello?
Yeah, this will only give the right column, right? Like most column you'll get something.
Yeah, so 0 multiplied by, -1 multiplied by 0 goes, disappears, -2 disappears, disappears. 0 multiplied by this one disappears, disappears, disappears. We only get 1 multiplied by 75, 2 multiplied by 80, and 1 multiplied by 80. And then we make the summation of these. Of course, if we had values here, we make the summation, and we put the value here. Can you tell me for this value, which 9 values does it correspond to?
You move it to the right.
Yes, so we start from which number?
25, 25, 75, and then you go all the way to 80. Yeah. That.
Nice. Now let me ask you a different question, right? Let's go back, clear all. For this one, which values should we use?
You go down one and you go right once.
Okay, so
start with 75 second row.
Nice, very nice. That's it. This is just what I wanted to confirm. So now you know how to apply the convolutional operation, which is, as we said, a sliding logistic regression, right? So it's just logistic regression, but now we slide it through the image, correct?
What if we want to put values, say on top of 235? What about the, where do we take this?
You mean here?
Yeah, suppose there, like we'll have to go up, but there's nothing up there. I mean,
you use sliding.
Amazing, amazing question. Very well. So let's continue the same type of question that we had before, right? So what do we put in this column? What do we put in this point?
You go right twice.
So 75, right?
Yeah.
So we finished. What should we do? We go down here and work on this column, right? And we put the value here, 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 and value here. So the rest of these are completely empty, right? We cannot calculate them.
Yep.
So the first thing you notice is the dimensionality of the input is bigger than the dimensionality of the output.
Yeah.
Very well. So this is one feature of convolutional neural networks, is that they reduce the size of their output is smaller than their input. Nice. Now, if we wanted to keep the same, what is it called? Keep the output, let's say I want to fix the shape of the output to 5 by 5. how much should I increase this image? Let's say I might be able to add more like empty values here, like zeros. How much should I add in order to keep it the same? This question is again for Randall. Huh?
5 plus 1 times 5 plus, I mean, n plus 1 times n plus 1, whatever the input is.
So previously it was 5 by 5, and it dropped up to 3 by 3.
Oh, that's 3 by 3. Okay, sorry.
So if I want to have something 5 by 5, the input should be
7 by 7. Yeah.
Very well. 7 by 7. Very good. So this is just to make sure that you have the intuitive understanding of convolutional neural networks. Now let's speak about the thing that we have just said, but more formally. So here we are going to speak about, sorry. Somebody forgot his, okay. Filling pixels, which are, yes. So what is padding, right? So padding is filling pixels around the input image in order to make the output bigger, right? So let's say, for example, that we are trying to increase the size or make sure that the output size remains the same as the input throughout the different layers. So this is 1 convolutional layer, this is 2 convolutional layers, this is 3 convolutional layers, and we want the size to be always the same. For this one, we're going to use, as we said, padding. Now, a very important question would come out is, why do we want the size to stay big, right? Why don't we want the size to be smaller? Because smaller images are easier to work with, meaning the training will be faster and the inference will be faster, and the model does not have to be very complicated to give us good results. So this is a problem when you have, like, let's say, small input images, and you would like to build a very deep neural network, right? So imagine, as we said, the bigger the neural network, the deeper the neural network, the better the performances should be. So if you would like to have a neural network of, for example, 12 layers, you should be able to still continue have some sort of an image even after the 12th layer. So this is why we usually use padding. So we use padding to keep the size of the output a bit bigger in order to allow us to build a much deeper neural network, meaning a neural network that is able to understand more complicated concepts and basically give better performances. So this is the reason why we apply padding. So again, in padding, so what we are trying to do is augmenting the size of the output or increasing the focus on the borders. So usually the borders are quite useless for us because the image is like this, right? So here is the cat, let's say cat. So usually the cat is in the middle of the picture. So all of this border really isn't important in this kind of images. But for some reason, if you are working in a case where the important information is exactly here in the border, in these cases, you might want to apply padding. So basically here, in this way, what is it called? Convolutionals will take into consideration the content of the border multiple times, right? So the convolutional operation will look into the content of the border multiple times, and this way it allows you to increase the focus on what is inside the border. So padding or adding more pixels around the input image is very useful. One, to increase or augment the size of the output, meaning it allows you to continue to have a certain image, like some dimensionality, even after applying 12 layers of convolutional neural networks, meaning you will have a better model that is able to understand more complex, what are they called? More complex concepts. And if you would like also to focus or increase the focus on the border information. Now, the second part is kind of the opposite. So this is called a stride. So stride basically is how much are we jumping, right? So let's say we had our first, this is our image. This is our first spot. If we're going to just move 1 pixel to the left, then we do this, right? But who said that we can only move 1 pixel, right? Why not move 2 pixels or move 3 pixels, right? So this is definitely in our, what is it called? In our capabilities. And this is what stride is. So stride is the jump size of the kernel on the original input image, right? So basically, by default, we are jumping only 1 pixel during the calculations of the convolutional operation. But if we want to jump 2 pixels or 3 pixels or 5 or 7 pixels, nobody can tell you no, right? So what is the effect, or what is the interest of using a bigger stride than 0? So the interest is simple: reducing the calculations and reducing the size of the output. So remember, every time that we apply this rectangle or this kernel on the input image, we get an output inside our output image. So if we reduce the number of logistic regressions that we apply, or reduce the number of kernels that we apply, the output image will be much smaller, right? And this is the interest. So this could allow you to simplify or make your model much faster, right? So this is why we use strides. Again, to summarize, we have presented 2 different applications or 2 different, let's say, techniques. First one is padding, which makes the output bigger. Second one is stride, which makes the output smaller. Now let's go and see how each one of these operations will influence the output size. So this is the dimensionality of the output. This is the dimensionality of the input. This is the padding. So the bigger the padding, the bigger the output. This is S. So you can see S is being divided on. This is the stride. The bigger the stride, the smaller the output. And here we have the bigger the P, or the padding, the bigger the output. Now for the K is the size of the filter. Remember that 3 by 3, it can be 7 by 7, it can be 8 by 8, 5 by 5, as you wish, right? So the bigger the K, the smaller the output. And this is basically the function that combines everything together. This one is called rounding down. So basically, if you have 5.9 in this formula, it becomes 5 because of this operation, right? So this is called rounding to the floor or lower. So 5.9 becomes 5, 5.2 also becomes 5, right? So we just take the integer that is first here. Okay. Just to confirm, how much time do we still have? Check. Oh, okay.
It seems
okay,
like
okay.
3 minutes.
Okay, so I thought we still had like 1 hour and 3 minutes. Okay. So for now, let's finish the lecture here. What we have seen so far is convolutional neural networks. We have seen padding, we have seen stride, and we have seen the dimensionality of the output. So let's call it a day off. Like let's call it let's finish. And next week, basically, we will have a small quiz about the different concepts that we have seen. We will repeat this final part of the dimensionality of the output, and then we will continue the lecture of convolutional neural networks. And from there, we will go to our first lab, in which we will have our, in which we will cover the different applications or different ways to build neural networks in PyTorch. Of course, maybe we will go a bit slow because we have Randall with us. And if he can learn a bit faster, then we can go ahead and finish quicker. Okay. Nice. So thanks a lot, everyone.